Okay, so let's look at this. Oof. Caleb, did you see this in the videos, in the YouTube videos?
No, I don't think so.
Uh-oh.
Didn't get there.
Okay, so I'm going to again give you, let's say, 2 minutes to think about this. I don't necessarily think everyone will kind of figure it out, but at least take 2 minutes just to think about what's happening here. I'm going to tell you that this is very, very similar to the previous problem. Now, if it helps, if you have, say, a graphing calculator, or if you're just on your laptop, you can go to wolframalpha.com. You might want to graph this function first, and that might give you a hint of how to proceed. Okay. All right, so try to discover the solution on your own without me telling it to you first. But it's okay if you don't, because we'll go over it. Okay, so let's see. So again, I don't expect everyone to have solved the problem. But in those couple minutes, especially if you graphed it, does anyone have an idea of how to solve this? Or did you notice anything about this function that's kind of peculiar? What are we thinking? What are your thoughts so far about this limit? So Jacqueline suggested make it into a piecewise. So can you make it into a piecewise? So what suggested that to you? Why did you think, why are you thinking piecewise function? Because of the absolute value. Okay, good. So first of all, absolute value typically tells you that there is some sort of piecewise function. Kevin says the function x equals 6 is in 2 different points. Has an asymptote at x equals 6? Well, actually, there is an asymptote at x equals 6. But actually, let's see what's going on here. So here's Wolfram alpha, right? So let's just actually plot this. So plot y equals absolute value x minus 6 over x minus 6. And let's say from x equals, let's say 3 to x equals 9, kind of around x equals 6. And let's see what it gives us. So it gives us this function. So this is a graph of that function, right? And we can see at x equals 6, there's this sort of jump in the function. Now, it doesn't really show it to you very well, but there should be an open hole at the end of each of these line segments. Because at x equals 6, this function is actually not even defined, right? So there is no value at x equals 6. But this very strongly suggests a piecewise function. This looks like the function kind of has two different formulas or two different forms to the left of x equals 6 and to the right of x equals 6. And it's very, very peculiar. It even looks like the function is just a constant on either side. Right, exactly. So Josh has actually kind of also said, I think I saw Thomas say it also, suggests this absolute value, there's kind of this plus or minus business, right? And Josh has said to the left of x equals 6, the absolute value turns everything negative. So that's why we get this negative 1. And to the right of x equals 6, there's something about it being positive, right? So there's this issue at x equals 6. So let's see this now in a bit more kind of analytical detail. Let's go back to the presentation. So what do we want to say here? We want to say something like, let's recall the absolute value definition. So let's kind of make that clear to everyone. Right. Absolute value of x is a piecewise defined function, right? We use these special symbols to kind of mean this function because it occurs so often, right? Absolute value of x is equal to, so why don't you tell me? If x is already a non-negative number, what is absolute value of x equal to? It's just x, right? It's just the same exact thing. What if x itself is a negative number? What expression should I put here? What expression is equal to absolute value of x if x is already a negative number? Negative x, right? So what does this mean if I were to kind of just stuff in an x equals 6 or x minus 6? So absolute value of x minus 6 is equal to what? Well, it's equal to, first of all, it depends on whether x is bigger than or equal to 6. Right? So the main thing about absolute value is what? If the inside of the absolute value, if the expression inside absolute value is already positive, you don't need to do anything, right? You just take off the absolute value bars. So if x minus 6 is already a positive number, I don't need the absolute value bars. Now, if x minus 6 is a negative number, that's the same thing as saying x is less than 6. If x minus 6 is already a negative number, that means the inside of these absolute value bars that is already a negative number. So to make sure that the absolute value returns a positive number, I need to take the negative of that, right? Negative, negative makes positive. So I get negative x minus 6. This is very important that everyone kind of understands that, right? That absolute value is a piecewise defined function, and really what separates the two pieces is the inside of the absolute value positive or is the inside of the absolute value negative? And in general, what I like to do is as a shortcut, you think you are always allowed to remove the absolute value bars, but you might have to put a negative sign on it if you're dealing with, say, if that thing were already a negative number. Okay, so what does this mean for our limit exactly? It means that, as a few students had suggested, can you explain again how you got negative x minus 6? So this is just this definition right here, right? Again, what is the definition of absolute value? The definition of absolute value says what? It says if x is already a negative number, right? If the inside of the absolute value is already a negative number, that means I need to put a negative sign on it. Why do I need that? Because the absolute value always returns a positive number. So if x is negative, minus x is a positive number. Now, going back to the x minus 6 business, it's the same principle. If the inside is negative, if x minus 6 is negative, that's the same thing as x less than 6. And if the inside is already a negative number, that means the absolute value is equivalent to putting another negative on top of that, right, to force it to be positive. Yeah, this is something that everyone kind of has to get used to with absolute value, right? Absolute value is equivalent in many contexts to an algebraic function, but sometimes you have to put another negative sign on top of it to make sure you get the right values. Okay, so in terms of the original limit, that means x equals 6 is a transition point for this function. So that means for the original limit, we should examine one-sided limits. And let's try to do this a little bit quickly now that we kind of have an idea of what's going to happen. So let's look at the left limit and let's look at the right limit. Okay, so the lim as x goes to 6 from the left side of this thing. So let's be very careful here. If x is approaching 6 from the left, right? This means that x is less than 6. So that means, so x minus 6 is negative. So if x minus 6 is negative, that means the inside of the absolute value bars are negative. So that means I am allowed to remove the absolute value bars, but because that number is already negative, I need to put another negative on it to force it to be positive, right? That's the main thing about absolute value. Now, once you realize that, the rest of the problem is very easy, but that's that's the hard part of the problem, realizing you can actually do that. So I get negative x minus 6 over x minus 6. Then I could say, okay, these things cancel out. And I'm left with what? Just negative 1. And the limit of a constant is just the constant. So I just get negative 1. Jacqueline, you have a question? It's okay if you don't. I'm goof. I'm good. And let's see what happens with the right limit, right? Something very, very similar. Lim as x approaches 6 from the right. But now what do we argue? We argue, okay, if I am approaching 6 from the right, all right, this means that x is bigger than 6, which means my expression x minus 6 in the absolute value is positive. Now, the nice thing about absolute value is if you're taking the absolute value of a positive number, you don't need the absolute value bars, right? It's the same exact thing, right? So absolute value x minus 6 is just the same thing as x minus 6, but only in this case, right? Notice very crucially how we use the fact that we're coming from the right, right? We're using the fact that x is bigger than 6 there. Okay, so I can just remove the absolute value bars. They don't matter in this case. And then we get these things cancel out. I'm just left with 1. And so my limit is just positive 1. And now we conclude this is exactly what we saw on the graph, right? Coming from the left, everything was negative 1. Coming from the right, everything was positive 1. And they don't match up, so therefore the limit doesn't exist. Any questions about this problem? So absolute value bars can be tricky. We're going to come back to these again on next Tuesday, or Tuesdays and Fridays lecture next week. We're going to have some more examples with absolute value. Okay, so we have about 10 minutes left. How did you get 1 again? Well, I got 1 in 2 places, so I'm not exactly sure which one you're looking at, but the first one comes from just cancellation, right? The second one, technically this is actually direct substitution property. But I feel if I had said that, that might have confused some people. The function 1 is actually a polynomial. It's the constant function 1. No matter what you plug in, you just get back 1. So the function 1, I plug in x equals 6 into that, and I just get back 1. So strictly speaking, I'm using the direct substitution property there. But I think sometimes some students kind of get that confused because it's a constant function. So I like a lot of times just to say the limit of a constant is the constant. But it does come from direct